But that is the same concept. For example, if you remember that when we have lymph wave, and we have an incident wave, and due to the discontinuity of this wall, we have reflected and transmitted wave, transmitted and reflected and PI, and this can be regarded as what? One is blood pressure, that is 2 pi, plus the radiation of lymph wave, harmonic radiation of lymph wave, right? You remember that. So what I basically said is there are two ways to explain what's going to happen when we meet the impedance mismatch in 2 dimensions. There are 2 ways. One is, okay, there's an incident wave, then due to impedance mismatch, there's a reflected wave, and then transmitted wave. Okay, or you could say that, okay, because of the impedance mismatch in space, there will be a blood pressure field and a radiated pressure field. Right? Same things we apply to the scattering problem or diffraction problem. So now you can have a sort of unified concept, right? So let's apply the same concept over here. This is the wave due to the reflection, or you can say this is the wave due to the radiation from that obstacle. Okay, the field over here will be superposition of this wave and this wave, and that results this wave. Okay. Right? Okay, let's see another case. We have small obstacle over here, and then we have sound coming over here, and then there is a diffraction, and certainly it shows the shadow zone. Okay? Now, if we put some small scatter over here, then the shadow zone influenced a lot. Right? There is a wave, but here there's no wave. If I put this kind of things, the sound wave over here is quite different. Okay? What about over here? I send the signal, or the incident wave has some angle over here. Then the diffraction phenomena over here is quite different. And different over here. And let us why we see that kind of things from this lecture. Let's begin with I have slits that has a width B, okay, and then I set up the coordinates at the center over here, and this is the R observation point, and this is a theta, okay, and this is R0. R0 means the vector that describes the opening. In other words, the surface of impedance mismatch. And I denote this is I0. Okay. The sound radiated in this space. Okay. And right? Send incident wave in this direction. Okay. Then what will happen? Over here, there is a impedance mismatch. Over here, there is impedance mismatch too. Okay. But we can try to get some pressure field at position R using what? Using Kirchhoff-Helmholtz integral equation, right? So I can write, okay, I can get the pressure by integrating over S0. Okay. P R0 and dGdF minus G dP, yeah, integrating over the surface S0. Okay. And please see appendix 4. There is a detailed derivation, and the solution turns out to be interesting form. P, the pressure R and theta. In other words, this is R and this is theta. Is square root 2 1 minus J rho 0 C U0. U0 is the what is U0? U0. U0 is the velocity of the fluid particle at the surface S0. Okay, the velocity of particle over here, and it's U0. And then I have square root K over pi R e to the j k r. Okay. Then I have very interesting term that sine kb over 2 sine theta, that is the argument of the sine. Then I have kb over 2 sine theta. When I have a three-dimensional opening, this case, for example, I have coordinate y and x, and I have z over here, and I denote, as you can see in the text, this is R, and this is theta, and this is the right angle. Then this is define the phi, and I am, and also I denote this is surface vector R0. Then define this is the angle, normal angle, phi n. Okay, then the solution as